Every second, billions of individual network requests, streaming video, database queries, and API calls converge on specific ingress points around the world. This architectural convergence forces massive volumes of data through a single entry point. The system responsible for distributing this incoming traffic is the primary bottleneck and the most sensitive single point of failure in a distributed system. In the late 1990s, managing this traffic required installing a physical hardware appliance in a server rack. If an organization needed more capacity, they purchased a larger piece of proprietary hardware. Today, a load balancer is a dynamic, programmable software layer operating at the network edge, running on thousands of commodity servers simultaneously. Scaling the software exposes a physical limit of computation. Pushing millions of packets per second through any centralized node consumes massive CPU processing cycles and creates latency as processor cores coordinate tasks. To maintain stability as traffic volumes increased, network engineers had to re-engineer the internal data path a server uses to process a packet. Survival at hyperscale requires abandoning physical appliances and traditional operating systems in favor of mathematical determinism and kernel-level programming. Every network architect must navigate a strict performance trade-off between Layer 4 and Layer 7 routing. Layer 4 routing operates entirely on network-level data. It reads the packet's 5-tuple header, the source IP, destination IP, source port, destination port, and network protocol. IP stands for Internet Protocol, the set of rules dictating how data is sent across a network. The load balancer makes its routing decision without ever looking inside the payload. Because it ignores the contents of the packet, a Layer 4 load balancer functions as a high-speed packet forwarder. It achieves microsecond latency with extremely low CPU overhead. Layer 7 routing operates at the application level, acting as an application-aware reverse proxy that understands the content of the user's request. This sequence shows the difference in packet traversal. On the top, the Layer 4 packet is briefly scanned and forwarded. On the bottom, the Layer 7 packet is stopped for inspection. To read the payload, the Layer 7 load balancer must first terminate the initial TCP connection from the client. TCP, or Transmission Control Protocol, is a communication standard that enables computing devices to exchange messages over a network. Then, the load balancer computationally decrypts the TLS payload. TLS, or Transport Layer Security, is a cryptographic protocol designed to provide privacy and data security for Internet communications. Once exposed, the load balancer inspects the HTTP path, or gRPC metadata. gRPC is a high-performance framework used for communication between microservices. After reading these details, the load balancer must open an entirely new secondary TCP connection to route the packet to the backend server. Layer 7 provides intelligent routing flexibility, but this flexibility comes at the cost of massive CPU cycle consumption and latency generated by switching between kernel and application tasks. As traffic volume scales, this computational tax eventually forces engineers to find ways to route packets before they overwhelm the CPU. In the 2010s, traditional dynamic routing hit a wall. These algorithms required load balancers to share a synchronized state table, a central database tracking every active TCP connection, so any node would know where to send returning packets. At the scale of a global network, updating a shared database across thousands of active threads creates a bottleneck. Processors spend more time waiting for state table updates than they do moving traffic. Google bypassed this bottleneck by building Maglev, a software load balancer that eliminated the shared state table entirely. This is the Maglev architecture. At the network perimeter, an eCMP router distributes incoming packets across a cluster of independent Maglev software nodes. eCMP is a routing strategy where packet forwarding occurs over multiple paths with equal priority. Instead of checking a database, the Maglev scheduler calculates a specific mathematical hash based exclusively on the packet's 5-tuple header. This relies on consistent hashing. Because the mathematical formula is identical across all Maglev nodes, any node that receives the packet will calculate the exact same backend server destination. Calculating a fixed equation takes a fraction of a microsecond, replacing the latency of a database query with mathematical certainty. Consider what happens when a node goes offline. If a Maglev node suffers a kernel panic, its active connection is severed. The eCMP router instantly detects the dropped BGP session. BGP, or Border Gateway Protocol, is the mechanism that manages how data packets are routed across the internet. The router immediately redirects those packets to a surviving maglev node. The surviving node applies the same math formula to the rerouted packet. The data reaches the correct backend server without the new node needing to consult a database to figure out where the packet was originally headed. By replacing active state synchronization with mathematical determinism, Google achieved massive fault tolerance and reached the throughput needed to saturate 10 gigabit network links using off-the-shelf commodity hardware. Even with optimal math, network speeds exceeding 10 gigabits per second reveal the next limitation, the Linux operating system itself. When a packet arrives, the operating system must allocate memory for buffers and process data through the network stack. Moving data from the kernel space to the application's user space demands a significant CPU cost. Meta bypassed this by utilizing eBPF in their open-source load balancer, Katran. eBPF is a technology that allows developers to run sandboxed bytecode safely inside the Linux kernel space without changing the kernel source code. Path 1 shows a traditional packet traveling from the network interface card at the bottom, through the kernel layers up to user space, and back down. Path 2 shows the eBPF shortcut. This shortcut utilizes an XDP hook. XDP, or Express Data Path, is a framework within the Linux kernel that allows custom packet processing at the lowest possible level, the network interface card driver. Katran evaluates and forwards the packet directly from the driver level before the Linux kernel is ever allowed to allocate memory for the data. This kernel bypassing technique allows a single processor core to handle tens of millions of packets per second. This approach is now moving beyond Layer 4. Frameworks like XLB bring Layer 7 microservices routing directly into the kernel's socket layer. In-kernel Layer 7 routing eliminates the latency of sidecar proxy architectures, which historically forced packets to bounce between the kernel and user space for HTTP inspection. True hyperscale efficiency requires treating the load balancer not as an external proxy, but as a logical extension operating within the operating system's data path. While the kernel optimizes individual packets, a different scaling challenge is emerging in GPU clusters training generative AI models. Standard internet traffic flows like millions of tiny streams, but AI training generates massive, synchronized transfers known as elephant flows. These massive data transfers are exceptionally sensitive to any network latency. Traditional routers evaluate flows based purely on the 5-tuple header we examined earlier. Because of this, a traditional load balancer views a massive elephant flow as a single, indivisible entity that cannot be split across multiple paths. Monolithic blocks forced onto a single link create hotspots, while adjacent links remain empty. Arista's AI-centric cluster load balancing inspects packets to identify distinct RDMA queue pairs, allowing direct memory exchange. It dynamically slices these data blocks across multiple paths, utilizing all links evenly. In synchronous AI training, stranded GPUs waiting on data flows cost millions of dollars in idle compute time. This RDMA-aware routing increases network utilization from 90% to over 98%, directly preventing those idle cycles. As the digital economy shifts from discrete web requests to massive AI training runs, the load balancer has transitioned from a standalone hardware component into a dynamic software system that sets the maximum throughput of the modern internet.